Hi everyone and welcome to the internet. So what we're going to be doing in our triple physics lesson today is having a look at currents and forces. So hopefully by the end of this lesson what you'll be able to do is describe Fleming's left-hand rule and also hopefully use it to be able to answer some questions. First thing I'd like you to do though, as always, is in your books there are 3 questions there on the screen. I'd like you all to have a go at writing down the answers to those in your books. So I'm going to give you about 3 minutes to have a go at answering those questions. Off you go. Okay, let's see how we've done. Obviously, tick them if you got them right for me. So for our first one, we should have said we could use a plotting compass or iron filings. Now you may have got into a bit more detail about how to do this, but as long as you've got use a plotting compass or iron filings, then you got your mark there. For our second one, to describe how we could use a compass to show the magnetic field of a current carrying wire is larger than the field strength of the Earth, then what we would do here is place a compass near the wire when there's no current flowing through it, and it will point towards the north. If we then turn the current on in that piece of wire, what we see is the needle then moves. Therefore, the current carrying piece of wire must be generating a stronger magnetic field than that of the Earth. And our third and final one then, looking at the shape of the magnetic field we generate around a single piece of wire, then we should have a series of concentric circles, so circles one inside the other. So make sure you've got at least 3 to get the mark for that one for me. So give me a tick on all of those, and then in the chat window just give me a little bit of an idea about how we did, who got 3, who got 2, who got 1, and I'm really hoping nobody got 0 today. So let me know in the chat window. So what we're going to be looking at today is what's going to happen if we place that current carrying piece of wire into another magnetic field. So if we start with the basics first of all, then anytime we place a current carrying wire inside another magnetic field, then we're going to get an interaction between the two magnetic fields. Hopefully we remember from our previous work that anytime a current is flowing through a piece of wire, that piece of wire generates its own magnetic field. So if we then place that into an existing magnetic field, there's some kind of an interaction that's going to take place. And what's really going to happen here is those two magnetic fields are going to be pushing on each other, and as a result of that, we generate a force on that piece of wire. Now, that force on the wire is always going to be at right angles to the magnetic field. So make sure you've got those 3 points written down. I'll give you just another minute to get that done. So get those points in your books for me now. If we now take a moment to think about what's going to happen with that interaction, if we've got two fields that are in the same direction and we put them together, then they're going to add up. We're going to get that cumulative effect. Whereas if those two fields that we're putting together are in opposite directions, then they're going to cancel each other out. So hopefully that does make sense, that if we put two fields in the same direction together, then they're just going to increase the effect. Whereas if the two fields are in opposite directions, they will cancel each other out. Let's start off by having a look at the diagrams I've given you on the right of the screen there. So towards the left of our diagram, we can see that we've actually got the kind of physical items, if you like. So we've got our current carrying piece of wire going through a piece of card in that instance, so we can see those field lines. And then underneath, we've got our magnet, which is showing us the north and south there. What we're going to do is we're going to put those two things together. So we're going to drop that bit of wire into the actual magnetic field of the magnet beneath it. Hopefully we remember that when we're talking about a single piece of wire, as we've got in the top there, then the magnetic field lines that current carrying wire will generate are the concentric circles. So we can see that in the top diagram on the right hand side. The X in the middle represents our piece of wire, and then we've got the circles representing our magnetic field with the arrows showing the direction it's going in. Underneath, we've then got the same magnetic field lines for our magnet. So you can see in that case there's just straight lines all parallel to each other, and we've got the field lines with their direction there. Now what we're going to be doing here is we're going to be putting that piece of wire into the magnetic field lines of the magnet. And when we do that, we get the diagram at the bottom. So you can see in the middle at the bottom there, we've got that thing that's labelled as a catapult field. So what we're really doing in that instance is when that piece of wire is in, and you can still see the piece of wire as the cross in the middle, then those circles that were lovely perfect circles all nicely spaced out, they've all become squashed and distorted. So you can see that they're kind of stretched down into more kind of ovally shapes. And those field lines that we had that were perfectly horizontal lines from our actual magnet, you can see that we've now got a bump in them. So what we've done there is we've stretched the field lines. Now what we can see is there's actually fewer stretched field lines beneath our piece of wire than there are above. Now what we're going to see in this case is the whole thing that's going to be happening there is those field lines want to straighten up. Okay, so in order to do that, that piece of wire is going to be pushed down to make those field lines shorter and straighter. So what we're really looking at here is how can we shorten those field lines, and that's going to give us an idea about the movement. So hopefully that does make sense to you. If you want to do any of the sketches and jot down those points, then I'll leave this one up just for another 30 seconds, so that if you want to sketch anything, by all means feel free. And obviously if you need a bit more time after that, you could always hit pause on the video now. So I'll leave this up for 30 more seconds and then we'll move on. Now, one of the things that they're going to potentially ask you to do on your exam is to describe the movement of these wires we're sticking in magnetic fields. And in order to do this, we need to know this thing called Fleming's left-hand rule. So I've given you a picture here, and I've given you that little reminder about the most important point of this next section is use your left hand. It's not called Fleming's left-hand rule just for giggles. It's actually because we are going to be using our left hand to work this out. Now, what we're going to see is that you've got those three fingers we're going to be looking at: your thumb, your forefinger, and your second finger. Okay, so as I know I've already said in class, then one of the key things you're going to have to know for P4 is the difference between your right hand and your left hand. If you don't know the difference between your left and your right, it's going to go badly in a lot of cases, I'm not going to lie. So let's start by making sure you know the difference between those. Now, what we're going to be looking at today is Fleming's left-hand rule, as we've said. So, needs the left hand. Okay, so when we're looking at Fleming's left-hand rule, this is where you're going to be contorting your hand in slightly strange ways, but it's all going to help you to answer these questions. So what we're going to do is we're going to start off with our hand, stick your thumb up. Okay, so we've got our thumbs up. Then your first finger, extend it out, and then for your second finger at 90 degrees, as much as you can get with 90 degrees anyway. So this is what you should have, okay? So this is how we set up our hand for Fleming's left-hand rule. Now, what we've actually got then is your thumb is going to be the direction that things move in. Your first finger here, okay, this is going to be your magnetic field, and it's going from north to south. Okay, so it points from north to south that way. And then your second finger is the direction the current is going in, from positive to negative. Now, what you're going to have to do is obviously move your hand around. Remember, we can flip upside down at this point to get it so it points the right way. So when we're actually looking at these questions, have your hand like this and then start with this finger. Okay, so what we're going to do is that's going to line up with the field line. So which direction, wherever the north pole of the magnet is, have the main body of your hand and then point towards the south pole. Okay, basically it's either going to be going that way or that way, okay, on the piece of paper. So you're pretty much doing that or that in terms of your actual directions north to south. Now, what we then need to do is make sure that our current is going in the right direction, okay, so from the positive to the negative. So in order to do that, you've got to be able to visualize these three-dimensional diagrams. It's not the easiest thing for everyone to do, but if it's pointing kind of into the paper, then what we need to do is make sure our hand is also pointing into the bit of paper. And once you've got that, your thumb will be pointing in the direction it moves in. So what we need to do is, using your left hand, is practice this, okay? So it does feel weird, okay, and I wouldn't suggest you try and hold that position for any length of time because it's strange. But you can just practice at lining this up north to south, positive to negative, and then this tells you, does the actual wire move up or does it move down? And usually what you're going to find is, on the exam, if it asks you the direction of the movement, it will either be up or down in this case, okay? We are going to look at this in a bit more detail in terms of directions in other devices in our future lessons, but the key for today is to get the understanding of how to use Fleming's left-hand rule and how to align your hands to get it right. What I've given you here then is an example of the kind of question that they could give you. So you can see you've got the diagram in the middle of your screen there showing you the direction of the field lines between your magnet, north and south. We've got our current carrying piece of wire with the direction of the current labelled into it. What I want you to do is, using Fleming's left-hand rule as we just saw, have a go at working out the direction of the force. So what direction will that wire move? Up or down are your two options here. So have a go at this. You need left hands at the ready. Give it a try. I'll give you about a minute to have a go and then write your answer into your book. Okay, let's see how we did on that one. So left hand should have been at the ready. Now in that one that I've given you on the screen, then we're going from north to south. So we're pointing north to south. Then our current is going into the screen. So we needed to have our hand going this way around to show our current going into the screen, as it were. Which means our thumb is then pointing downwards, so the correct answer is down. So hopefully Fleming's left-hand rule does make sense to us and we can use that to work out the direction of the force. Now, the last bit that we need to understand in this lesson is how we can actually calculate the size of the force that's going to be acting. Now, what we've got on our screen at the moment is the formula that we need. So the force on a conductor carrying a current in newtons, because all forces are measured in newtons, is the magnetic flux density, measured in Teslas, times the current in amps, times the length in meters. Now, bit of good news for us again, this is one of those equations, one of the very, very few, that the exam board are guaranteed to give you in the exam. This is going to be one of those that you find on that formula sheet in any physics paper. So you don't have to memorize it, you just need to be able to use it. And remember, the formula sheet exists, of course. Now, what we're going to find then is, when we're considering the size of any force, then quite clearly from that formula at the top, we can say it depends on three things. What I want you to do is just fill in those three things the force depends upon. So write those down in your book for me. I will just give you about another minute to get that done for me. Okay, let's just make sure we did get those right three things written down. The size of your force will depend upon the magnetic flux density, the current, and the length. Hopefully we managed to work that out from the formula at the top, because if our force is magnetic flux density times current times length, those three things are going to determine the size of the force. So tick them if you got them right. If not, obviously fill them in. So magnetic flux density, current, and length. As always, when we've just been introduced to a formula, the next thing we're going to do is have a go at some calculations. So there's 4 questions on the screen for you. Show your working, remember. Do not just write down an answer you've got from a calculator, because silly errors mean no marks at all. So write down the formula, substitute into the formula, solve it with the answer. So 4 questions, show your working, in your books, have a go. Okay, so let's see how we can actually solve these then. Hopefully we do all remember force is magnetic flux density times the current times the length, as we've already established. Now what we need to do then is go through. So if we start off with question 1, then what we're told is the magnetic flux density is 0.75, The current is 3 amps and its length is 0.1 meters. So quite simply, all we need to do is substitute those into our formula. So our force then is going to be 0.75 times by our current, which was 3, times by our length, which was 0.1 meters. And if you type that into your calculator, I'm hoping that you came out with 0.225 newtons. So excuse the terrible handwriting on this, I'm still getting used to this new little tablet thing. Now our next one, again, it's just using the exact same thing. So it's still force is our magnetic flux density times the current times the length. In this case, our magnetic flux density is 0.5. So it's going to be 0.5 times our current, which in this case was 5 amps. And then we're going to times that by our length of 0.5 meters. So when we've done that, we should end up with 0.25 newtons. Now for number 3, it wasn't quite as easy. I couldn't give you all easy ones. So on this one, we're actually working out the current. So we need to rearrange this equation here. Now I've given you a triangle at the bottom. It's very similar to the ones we've seen before, except there's 3 things at the bottom. So you've got your magnetic flux density, the current, which is given the symbol I, and our length, okay, and then our force at the top. So if we actually want to find the current in this case, okay, so if we're solving for current, my handwriting is terrible, I'm sorry, then this is I, so we just cover that bit up. Now what that leaves us with is force divided by the magnetic flux density times the length. So current is the force divided by magnetic flux density times length. Then what we can do is substitute those values in. So our force was 0.32 newtons, and we divide that by 0.3 for our magnetic flux density, and we're going to multiply that by our length. Go careful though, because the length was given to us in centimeters in the question, so we need to do that as meters. So divide by 100, and when we've done all of that, we should end up with an answer of 5.3 amps. 5.3 recurring, but 5.3 is fine. Then for the last one, we're solving for length in this case. So our length is force divided by, same thing as we did before, cover up our length over here. So it's force divided by magnetic flux density times our current. And we can substitute in our values. So that's going to be 0.5 for the force divided by our magnetic flux density of 0.2, and our current was 8. And when we type that into our calculator, hopefully we did get an answer of 0.3125, and that's in meters. So hopefully that all makes sense to you and you got those right. So tick the ones you got right, have a look to see where you went wrong on the other ones. I'm guessing some of us may have forgotten to do this conversion to meters rather than using the centimeters. And let me know how you've done in the comments. Give me a score of 1 to 4 now. As always, just to finish off then, we've got our plenary questions. Up to grade 5, it's the 2 on the left. More than a grade 5 is your target, it's the 2 on the right. Don't forget you can find the answers on the website. So I'd suggest you pause the video here to have a go at doing these, because I'm not going to be leaving it up for that long today. As always, don't forget you can get the answers to the plenary and some additional work to be getting on with on my website. The link is on the screen for you. Now, because we're about to hit our Easter break, then we won't be having physics next Friday because that is part of our Easter holidays, but we will be back with more triple physics after the Easter.